Okay, so we're going to talk about the extreme value theorem. So before I continue, just in case you are new to the channel, uh, do well to subscribe, ring the notification bell, so that each time we upload new content, you'll be notified. We have a lot of exciting content that is coming up, both theory and something that some stuff not really practical engineering like practical, but at least to try to see it in terms of theory for now. Then when we have our hands on something that is practical, we'll try to bring it to you guys. Okay, so when you talk about the extreme value theorem, of course you're still talking about multivariable functions. Okay, so what it is that the only one of the things that you really have to keep in mind when talking about the extreme value theorem, all we are determining is either the relative mean, okay, or relative maximum. Okay, so we'll talk a little bit about the relative mean as well as the relative max, and also talk about the second, okay, the second partial test. All right, so the second partial test is really an interesting tool that we use to determine whether we have a relative mean or relative max. And again, we have to keep in mind that when you have when you don't have a relative mean, you don't have a relative max for a given function. Okay, and again, we are talking about functions of two variables in this case. When you don't have a relative mean and you don't have a relative max, what you're going to have are what are saddle points. Okay, uh, you're going to have saddle points. So as saddle points really come about when you do, like the coordinates that you have, they don't give you a mean, they don't give you a max. What they give you is something that is not a max, that is not a mean. So we are going to classify that as a saddle point, and you're going to understand that when we talk briefly on the second partial test. It's a very interesting part of the extreme value theorem. Okay, so what is this extreme value theorem? What are we able to understand, or what should we understand, so that at least when you're answering questions, like you have that confidence because you really know what you're talking about. Because answering questions is just it's not just about answering, it's about you understanding what you are doing. Because let's say you do some examples from a past test paper, exam paper, a tutorial sheet or something. It might not really come the same way in another assessment, but if you really understand the theory, it becomes much easier for you to handle it, no matter how it comes. Okay, so when talking about the extreme value theorem, we're going to say let f, okay, let f be a continuous function of two variables. Let it be a continuous function of two variables, x and what, um, x and y. Okay, x and y. So we are going to let f let f be our function, that is let f be a continuous function of two variables x and y, and that is defined on a on a that is defined on a closed region. Okay, that is defined on a closed region that I'm going to name as R. So this our f needs to be a continuous function of two variables x and y that is bounded by a region that I'm going to name as n in the xy plane. Okay, so now if this is what we have, if this is true, we're going to say for the function f, there is at least one point in the region n where f takes on a minimum value. Okay, so now if this what we have said here is true, there is a point at which within the region n, okay, our f uh, takes on a what, takes on a minimum value. Okay, so and again there's also at least in this case, like there can be multiple points that you can have. And to understand that better, when you start to try to determine what critical points we have for a given function, and I say within the bounded region n, okay, our f takes what, takes on a what, a maximum value. Okay, so here I'm not just talking about because, like, let's say this is our z, that's our y, that's our x, we have a surface, something like that. So you find that we are saying if this is true, then within that bounded region, our f there's at least one point, okay, at least one point, meaning there can be multiple points where f takes on a mean. So meaning you can have multiple points that can give you a mean for that function f. The same applies to this second point. Within that that given region, there is at least one point where f takes on a what, takes on a maximum point. Okay, where you have the maximum value. Okay, so now what about the relative extrema? Okay, so now how do we then know when we have a relative mean, a relative max for a given function? Okay, how do we know? So now the thing is that if uh, if this same f, that the function that we have, from this statement, it's obvious we know that that f is defined in that region n that you have. Okay, it can be anything, but in this case I'm using n. It's the region n. Okay, if f is a function that is defined on that region n, that is containing some points. In this case I'm going to call those points x initial as well as what, as well as y initial. Okay, so here I'm going to say there, I want to try to show you when you have a relative mean as well as a relative max. Okay, so we're going to say my f. Okay, my f has I'll say it has a relative mean. Okay, relative mean at that point. Okay, at that point x initial comma y initial, if, okay, if my f of x, okay, f of x is greater than my f, greater than or equal to my f x initial y initial, meaning for the second part your f has a what, has a relative maximum uh, at those points x initial y initial, if your f of x, okay, your f of x is less than or equal to your f x initial y initial there. Okay, so now within that bounded region, if our x is like we have this our f that is bounded in that region that has the points x initial y initial. So if we are going to say f has a real mean, I mean have a relative mean, sorry, a relative mean at these points, if that is true, then at those same points f is going to have a relative max if that is satisfied. Okay, but this maybe might be a bit difficult for someone to really understand, but I'll try to simplify it using the explanation from the second partial test. Okay, so what we know overall that extreme value theorem, we're just trying to determine your minimum as well as your maximum. Okay, and we know to say it's either we have a relative mean, a relative max, or we can just have all of them as relative mean, or maybe all of them as relative max. Or if we don't have a relative mean, we don't have a relative max, meaning you have saddle points. Okay, so now one thing that we're going to be using when talking about the second partial test is this. Okay, so we're going to say let f be a continuous let f have a continuous second partial derivatives on an open region containing a point x comma b. Okay, so if your function f have a continuous second partial derivatives on an open region that I'm going to name as a comma b, uh, for which your fx, your meaning your the partial derivative of that function that you have with respect to x is equals to what, is equals to 0, more like you're equating the gradient function to what, to be equals to 0. So even your what, your f of y a comma b to be also what, to be equals to 0. So now what you need to do is that to test for relative extrema, remember to say when you say relative extrema, you're just trying to say, okay, is it relative mean or relative max, or perhaps you have saddle points. We are going to be using the discriminant. Okay, so in this case the discriminant, you're going to say your d will be equals to your f, um, your the second partial derivative of that function with respect to x, okay, with respect to x at those points a comma b, multiplied by what, the second partial derivative of that function with respect to y at a comma b, then minus uh, the mixed partial, we say xy here at that point a comma b, squared like that. Okay, so that's the discriminant that we have. So what we want to try to do now is that we want to know when we have a relative mean as well as a relative max. So the first point that I'm going to say, if my d, okay, if my d, the discriminant is greater than 0, and my second partial derivative of that function at the point a, um, at the point a comma b, if it is greater than 0, okay, then we are going to say f has what, f has a relative mean. Okay, I'll say relative mean at a comma b. Okay, so the second point we are going to say, if my d, okay, if my d is still greater than 0, and my second partial derivative with respect to x of that function at a comma b, um, if this is less than 0, then my f has a what, has a relative max at a comma b. Okay, so the third point, if my d is less than 0, and okay, in fact I don't even need to talk about the second partial part. And so if my d is less than 0, then uh, I'll say a comma b comma f a comma b is what, is a saddle point. So meaning among the critical points that you have, meaning that point that you are going to have is what, is a saddle point. Okay, so now the fourth thing is that the rest is inconclusive, and anything that is not part of what I've written here is inconclusive. Let's just say our d is equals to 0. Here I've talked about when our d is less than 0, meaning anything, any value negative, or maybe when d is greater than 0, any value not 0, starting from, maybe even starting from as low as 0.01. If it's like that, we can try to look from this and that. We try to see either it's relative extrema, I mean relative minimum or relative maximum. Okay, so let's try to look at some examples. I believe all of this is going to make a lot of sense when you try to go through these examples. So we're going to say the question is asking us to determine the relative extrema for our function f x comma y, which is equals to x to the fourth plus y to the fourth minus 4xy plus 1. So the first thing first that you need to do is that when you're trying to determine your relative mean and your relative max, first of all you have to determine the critical points. Okay, we have to determine the critical points. So the first, what you do that to determine the critical points, you have to determine your partial derivatives, both with respect to x and with respect to y. Okay, for that function that you have. So my f of my partial derivative of that function with respect to x is going to be equals to 4x to the third, okay, minus 4y. I'm keeping this as a constant and that as a constant, then they just become 0. Okay, then for y, fy x comma y, that will be equals to, we're going to get 4y to the third minus 4x. Okay, so now to determine these critical points, I'll set uh, my partial derivative with respect to x of that function to be equals to what, equals to 0. So meaning I'll say it's my 4x to the third minus 4y to be equals to what, 0 there. So I do the same for this side. So meaning I'm going to have my 4y to the third minus 4x will be equals to what, will be equals to 0 here. Okay, so what do we have? So I'll say this is going to be 4x to the third is equals to 4y. So the 4 goes and that goes. So I have what, um, I have x to the third being equals to what, being equals to y there. Okay, what about this part? We say 4y to the third is equals to 4x. what do we have? We're going to have the 4 going, and that 4, so we have y to the power 3 being equals to what? Being equals to x. Okay, so that's what I have as my what? That's what I have as my y, or more like saying my x is equals to y to the power 3. So I'll come here and substitute and see what I'm going to get. I'll say, okay, here we have x, I'm going to put y to the power 3, then I have a 3 there. Then I'll say that is equals to what? Equals to y. So this is going to give me something like, this is going to give me, that will be y to the power 9 is equals to what? Is equals to y. Okay, so what do we then have? Or do I really have to do this? Okay, yeah. So let me say now, I'll say y, okay, to the power 9 minus y is equals to what? Is equals to 0. Okay, how is this going to be? So I can factor out the y, that would be y, then y to the power 8 minus 1 is equals to what? Is equals to 0. So I'll say my y is equals to 0, or my y to the power 8 is equals to what? Positive 1, of which when you try to find what the exact value of y is, that will be equals to positive or negative what? Positive or negative 1, simply because you're going to say y is equals to the 8th root of what? Of 1. This is an even root, so meaning you're going to get the positive or negative there. Okay, so now the critical points that we have is like, for my y I have, for the y I have 0, I have 1, I have negative, I have negative 1. So what about my x? So it's just a matter of you replacing in the equation. We have said our x is equals to what? Y to the power 3. If you replace where there is y here, put 0, your x is going to be what? It's going to be 0. If you put 1, it will be 1. If you put negative 1, it will be negative 1. So meaning the points that we have 0, comma 0. These are our critical points. You have 1, comma 1. We have negative 1, comma negative 1. Those are our critical points. So they are the ones that you're going to use to determine whether we have relative mean, relative max, or perhaps maybe saddle points or something, or maybe we get something that is inconclusive. Okay, so those are the critical points that we have. I'll say critical points, CP. Those are what we have. So now we have to remember to say this is the point now where we have to bring back the where we have to utilize the second partial test. Okay, so the first thing that I'd want to do is that I'd want to find my the second partial derivative. So remember to say the partial derivative with respect to x, at x comma y. What we found was fx to the power 3 minus 4y. Okay, so if I want to determine the second partial test, what is it going to be? So the second partial test is nothing but, this is a constant, so what you're going to have is a 12x squared. Okay, so what about the other part? Your partial with respect to y, what we got was something like 4y to the third minus 4x. Okay, so differentiating with respect to y again, meaning giving us the second partial test, what you're going to get is a 12y squared. Okay, so now we also need to determine the what? The mixed partial, our fx. We need to determine our mixed partial, our fxy. Okay, that is at x comma what? X comma y. What is it going to be? What we mean here is that we are just differentiating the function that you have, which is this function here, okay, or that derivative that we got. Now you differentiate it with respect to what? With respect to y. Okay, so meaning you're going to keep this as a constant, and when you differentiate, you're going to get negative what? Negative 4, which is what you have right here. Okay, so now to determine the discriminant is going to be equals to, remember we said it's the second partial, okay, multiplied by second partial with respect to x by second partial with respect to y, but at the point, like at these points that we have. Okay, at those points that we have. Okay, so what I'm going to do is that, okay, I need to determine what my discriminant is. So I'll say at to determine the discriminant, uh, we already know what the formula is. We say it is d is equals to second partial with respect to x at the points. Now we are going to say, I'll just say a comma b, okay, by second partial with respect to y at a comma b minus uh, the mixed partial at a comma b squared. So now I'm going to say, first of all, I'll start at 0 comma 0. I'm just using the critical points that I have there. At 0 comma 0, what are we going to have? Our d is equals to what? Our d is equals to, if you get this function that we have, okay, if we get this function that we have, um, if we get that function that we have, then we substitute with where we have x, we put 0. That would be like we're going to have 0 by 0 minus, what do we have here? We have negative 4, where we're going to put for that one here, because that's what we get. So negative 4 squared is positive 16, but you're going to say minus 16, which gives us what? A negative, just gives us negative 16 as the value that we have. So now the thing is that, do we have um, do we have a relative mean or a relative max, or we have saddle points? So we have found that the discriminant is less than 0, but for us to conclude, we have to know what the value of this is, because that's how we compare, or that's how we determine whether it's a minimum or a maximum or a saddle point. So now you're going to say, okay, what is our f okay, what is our fx, okay, fx y, yeah, okay, let me say at the point 0 comma 0. Here we have 12. You substitute with 0, what are you going to have? You're going to have a 0 there. Okay, so that's what we have. So what we have found, that our d, okay, our d is less than 0, but our f, our second partial with respect to x is equals to 0. But remember to say, for it to be either minimum or maximum, it's supposed to be either greater than 0 or less than 0. For this reason, okay, for this reason, we can say this is a what? This is a saddle point, okay, because of what we have right here. This could have been either a maximum or a minimum if maybe this value that we have for that one is either less than 0 or greater than 0. But if it is equals to 0, we have to say it's a what? It's a saddle point, because it's neither a relative mean or a relative max. Okay, so that's what we get for that critical point. So let's try to determine for the other one. So let's say at the point 1 comma what? 1 comma 1, our discriminant is going to be, in this function that you have, okay, if you substitute with a 1, you're going to get what? A 12. In this function, you substitute with a 1, you're going to get what? A 12 here, minus, here we know we already have a 4, that is what? That is a 16. Okay, so this value here, what are we going to get? 12 times 12 is 144, minus 16, it gives us what? It gives us 128, and this value is greater than what? Greater than 0. But are we going to conclude to say this is a relative mean or relative max? Not just yet. We have to determine what the value of fx, or the second partial with respect to x at 1 comma 1 is. You get that this value is what? Is nothing but a 12. Okay, you get that the value that you're going to get is what you're going to get is a 12. So now this value that you have, it is greater than what? It is also greater than 0. Hence we have a relative mean at that point, because this is greater than 0 and the discriminant is also greater than 0. Okay, so now let's talk about what we are going to have at negative 1. Okay, so I'll just put negative 1 comma what? Comma negative 1. Our discriminant is going to be we are still going to say this is like if you substitute with negative 1 here to be positive, so it's simply the same. 12 by 12 minus 16, which will give you like 144 minus 16, which will give you something like 128, which is still greater than 0. If you come here and say f of x there, okay, at the point negative 1 comma negative 1, if you put negative there, you're going to get a positive. That would be positive 12, okay, which is greater than what? Greater than 0. Hence, we still have what? We still have a minimum. Okay, so what conclusion have we made here? Okay, what conclusion have we made here? By applying the second partial test, so at 0 comma 0, we have what? We have saddle points. Saddle point. So at 1 comma 1, we have what? So I'll say this is relative mean. Relative mean at negative 1 comma negative 1, we have what? Relative max. Okay, so it's very important that we keep this information very close to us, like how we come up with those. So let's try to look at another example to try to make sense out of what we are saying right here. Okay, so this one is the example we're going to look at is a bit different from what we had here. Here we just had something like a basic function. So now we are saying the question is saying find the shortest distance from a point to a plane. So we know that the distance from a point to a plane is just simply equals to the absolute value of what? A times x plus by plus cz plus d divided by the square root of a squared plus b squared plus what? C squared. But this gives me more like a maximum distance, but I'm talking about the shortest distance. So in this case, my goal is to minimize what I have. Okay, so we have this point here and this plane. How do we then go about that one? So to find the shortest distance, what I need to do, or what you need to do, is to minimize the distance from that point to that plane. Okay, so in this case, you're saying your distance overall, your distance is simply equals to the square root of x minus x initial squared plus y minus y initial squared, okay, plus z minus z initial squared, like that. Okay, so now I'm going to write this in terms of a function, but I'm not going to write it using a root. I'm just going to say it's, let's say f of x comma y comma z, which is going to be equals to my x minus x initial squared plus y minus y initial squared plus z minus z initial squared, like that. Okay, so from this plane that I have, okay, from the plane that I have, I need to try to write it in terms of so what I have here, this function is is a function of, like, we have the x, the y, and the z, more like a function of 3 variables. Now I want to write it as a function of 2 variables. Okay, it will be much easier for me to work with. So what I'll do is that I'll get this function, write it in terms of z, like make z the subject of the formula, meaning my z is going to be equals to 4 minus x minus 2y. Okay, so meaning here I'm going to come and say f of x comma what comma y, because that is going to change. So I'm going to have my x minus x initial squared plus y minus y initial squared plus my z, okay, minus no, I'm not going to use z there. I'm going to use the 4 minus x minus 2y minus what? Z initial squared, like that. Okay, so now I can try to try to simplify this. Okay, so now the thing is that here I have to substitute with the points that I have. Okay, so I have my x minus, what's my x here on the point is what? Is 1, so that would be like 1 squared. Okay, so I have my y initial is 0, so that just be y squared, so that would be plus. So here I'm supposed to say 4 here, then a 2 here. Okay, but it's a negative 2, that's going to become positive, so meaning you're going to have a 6 minus x minus 2y squared, like that. Okay, so remember to say we are using the second partial test to determine the critical points okay, determine the whether it's relative mean, relative max, but before that we have to determine the critical points. Okay, so uh, the derivative of that function now with respect to x, how is it going to be? When you differentiate what you have here with respect to x, I'll not really go through it step by step. I believe we are now familiar with how to go about it. What you're going to get is that this is going to be equals to 2x minus 1, okay, uh, that would be minus 2 uh, x minus that would be x minus 2y. Why is this a minus here? Because when you differentiate this with respect to x, you're going to get negative, so that would be, instead of a positive, to be a negative there. Okay, what about the derivative with respect to y? So that would be fy. When you differentiate, I believe you might get something like 2y minus 4. Then you have your 6 minus x minus 2y. Okay, I believe by now we are familiar with how to go about those. Okay, so remember to say, to determine the critical points, we just have to equate this and that to 0. So after you equate those to 0, what you're going to find is that your x will be equals to 1 over what? Will be equals to, sorry, it will be equals to 11, not 1, but 11 over 6. Then your y will be equals to what? 5 over 3. Okay, that will be equals to 5 over 3. So how then do we come up with okay, I believe we no longer need this one, at least for now. Okay, at least for now. Okay, so these are the points that we have found. Those are the points that we have found. How do we then utilize them? Those are more like our critical points. So first of all, I need to determine the second partial test. I mean the second derivative, the second partial derivative. So if you, from the first partial derivative that we have in respect to x, we said it was x comma y, which we found to be equals to what? 2x minus 1 minus 2, then 6 minus x minus 2y. Then with respect to y, it was something like 2y minus 4 here, then you have 6 minus x minus 2y. Okay, so to find the second partial test, okay, with respect to x, what you're going to get is something like with respect to x, what are you going to get? So in here you're going to get a 1, okay, so that would be like a 2 here. So in here you're going to get this will be, the 6 will be 0, the 2 minus 2y will be a 0, so you're going to get negative 1 uh, by that negative 1 there, I mean by that negative 2, you're going to get plus 2, giving you what? Giving us a 4. Okay, so we have a 4 there. So what about the second partial with respect to y for that one? You're going to get a 2 here. Okay, what about the inside part? So the inside part, this is going to give you 0 0, then you're going to get negative 2, negative 2 by negative 4, that will give us that's going to give us something like that's going to give us positive 8, of which when you add them you get a what? You get a 10. Okay, that's what we get. So I also need to find the mixed partial. Remember to say we are going to use it when you're using when you are finding the discriminant. So second partial, that, what are we going to get? Okay, so for the second partial, we differentiate this function with respect to y. What are you going to have? This, all of this is going to be a 0. Okay, so this will be a 0, that will be a 0. Differentiate this with respect to y, you're going to get negative 2. Negative 2 by this negative 2, you get what? You get 4. Okay, so tell me the discriminant. We're going to say this one by that one. It's simply, we're going to say 4 multiplied by the 10 minus square of that, that would be what? That would be 16. What do we get? This is you're going to get that's 40 minus 16, which will give you what? 24, which is greater than what? Greater than 0. So now what you observe is that the value for this is greater than what? Greater than 0, and the discriminant is also greater than what? Is also greater than 0. Hence you're talking about you having a what? Having a minimum. So this was just for us to confirm that we have a minimum, because you can't continue to find your distance if you have a maximum. Okay, if you have a, like you can have multiple critical points, but you need to determine which one is a minimum, because the aim here is that we are determining the shortest distance, and for the shortest distance we need a minimum point. Okay, so meaning now we can now determine what the distance is. So what you need to do is that you just get the same equation that we have for the distance. So what is our x in this case? We have found that it is 11 over what? 11 over 6 minus our 1 from the point, which is this one. Okay, then plus our y is 5 over 3 squared. I'm just using this equation here, that formula I mean. So plus my z is a what? Have we really determined what our z is? We have not yet determined what our z is. Okay, we have not yet determined what our z is. How do we determine our z? You can just substitute your value of x here. You can say it's 11 over 6 plus, that will give you, like, you put your y here, that would be 10 over, that would be 10 over 3 plus z is equals to what? Is equals to 4. Okay, that is we have a 6 here, that would be 11 plus, that would be a 220. We get, is it 31 over 6 plus z is equals to 4 there. Okay, so we're just trying to determine our z is in this case. Okay, so how is that going to be? That would be like z will be equals to 4 minus 36, sorry, not 36 but 31. That will be 31 over 6. We have a 1 there, so that will be z is equals to 4 times 6 is 24 minus 31 divided by 6. What are we going to get? Your z will be equals to your, like, 24 minus 31. What are we going to get? We are going to get something like oh, maybe without even, maybe we don't need to waste time to find what our z is, because we can say, okay, our z, we said our z was equals to what? Was equals to 4 minus x minus 2y there. Okay, so we just need to say, okay, our z is equals to, which is similarly the same thing anyway. So we say minus 11 over what? 11 over 6 minus 10 over what? 10 over 3. So which I can put here, my 4 minus 11 over 6 minus 10 over 3 minus, I'm supposed to say minus the z, which is a negative 2, but I'll say plus what? Plus 2. So when you finish here, you find that your shortest distance is going to be equals to 2.041 units. And that's what my shortest distance is. Okay, so let me try to look at the last question. Okay, hope we understand this one. Okay, so we are saying a rectangular box without a lid is made from a 12 meters cubic of cardboard. Find the maximum volume of such a box. So now the thing here is that we are just maximizing. Okay, we are just maximizing. So now keep in mind to say this is more like in the x, like this is in the x, the z, and the y plane. Okay, so now the thing is, the volume is nothing but volume is equals to uh, volume is equals to length times breadth times height, but we are talking about in terms of the x, the y, and the what? The y and the z there. That's what our volume is. Okay, so our volume is equals to x, y times what? Times z, like that. Okay, so of course this we can also we can also use Lagrange multipliers, and we'll look at this example under Lagrange multipliers as well, so that we try to see if what we are doing now is going to be the same as that of Lagrange multipliers. Okay, so now one thing is that I'm given the area, and if the box that I have is does not have a lid. Okay, it does not have a lid. So we say the box does not have a lid, so meaning it's open on the top. So it's more like you have a box that is in this form. Okay, so on the top here it's not closed, it's open. Okay, it does not have a lid, and you don't say this is your x. No, 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 that's my y. So I'll say this is my x, this is my y, and this is my what? That's my z. Okay, and that box that you have there, if it was closed on the top, you're supposed to have more like sides that are equals to, like this side equals to the other one, that's this side. Okay, this one equals to the other one. Okay, then the top one equals to the bottom one there. Okay, so in this case, to find our area, is just the area of each of the sides, then we add them together. So in this case, for the bottom part, I'm supposed to say 2xy, but I'm not going to say so. Why? Because the top part is what is not included. We are saying it's open, so it's just what? It's just xy plus. What about this part? When you approach it in that direction, is your sorry, this is my z. That's going to be your y, your 2y, z, like that. Y is because you have a one here and you have another one there. There are two of them. The same applies for this side. It's going to be what? It's going to be your x, z, but two of them. That will be equals to what? The 12, which is what? The area that we are given. Okay, so from this, for convenience's sake, I would want to deal with a function of since this is more like a function of three variables, we have your v, your x, comma y, comma z, which is going to be equals to your x, y, z. I'd want to deal with my v being x, comma what? X, comma y. What is that is going to be equals to? So that's x, y. I need to substitute the here with what? From this, I need to make my z the subject of the formula. My z is going to be equals to 12 minus xy divided by 2x plus 2y. So when you substitute here, we say 12 minus xy divided by 2x plus 2y, like that. Okay, what do we then now do? So this is same as what? This is same as just writing it as 12 xy minus xy divided by 2x plus 2y. Okay, so first things first, remember to say here we have to use the second partial test to determine what the maximum is. Okay, so the derivative of that function v, which is simply my volume, that is at x comma y. Okay, at x comma y, when you differentiate this with respect to y, it's up to you which method that you're going to use. Either it's a chain rule or the quotient rule is simply one and the same thing. When you differentiate, what you're going to have is something like a 24y squared minus 4x y to the power 3 minus 2x squared y squared divided by 2x plus 2y squared. Either use the quotient rule or the chain rule, you're going to get the same thing. Vy at x comma y is going to be equals to 24x to the second minus 4yx to the third minus 2x squared y squared divided by 2x plus 2y squared. Okay, so remember to say here, determine the critical points, hence you need to equate this to what? To 0. Okay, so now when we equate that to 0, what it is that you're going to find that your this will be equals to something like when you equate what you have here or everything, this part equals to 0, so you find that the denominator the denominator won't be that necessary. So I'm going to say I can factor out the y, that would be y squared. Then I have 24 minus 4x y, okay, 4xy is that really going to be 4xy? Yeah, 4xy, then that would be minus 2x squared, okay, 2x squared. And since this was equals to 0, I can even try to simplify it a bit further for myself. Like, instead of me, I can divide by 2 here, by 2 here, by 2 here, because I'm equating this to 0. Even if I say 2 here, yeah, so that is going to work out. So 24 divided by 2 is a 12, okay. So then the 4 divided by 2 is a 2xy minus the 2 x that you 2x squared that you're going to get. It's just supposed to be x squared, like that, okay. So we do the same on the other side. When you do the same on the other side, it's going to be x squared. That would be 12 minus 2xy minus y squared is equals to what? Is equals to 0. So here we observe that our y squared is equals to what? Is equals to 0. Or even here this side, our x squared is equals to what? Is equals to 0, making our x to be what? To be equals to 0 there, okay. So but we are not done. We can now say, okay, our 12 minus 2xy minus x squared is equals to what? Is equals to 0 as well, okay. So even on the other side, we can say, okay, our 12 minus 2xy minus y to the power 3 is equals to what? Sorry, to the power 2. The power 2 is equals to what? Is equals to 0, okay. So now what do we then need to do here, okay? What do we now need to do? So I'll get this function here, okay. It's my 12 minus 2xy minus x squared is equals to 0. So at this point, what I'll do is that I'll say, okay, I can write this as, okay, I can write this as what? This is the same as you saying your x squared, okay, your x squared minus your y squared being equals to 0. Why am I saying so? Because this part here that you have, this is more like you're saying your 12 minus 2xy is equals to what? Y squared. So this part here I can substitute with what? With y squared. That's why I'm writing it like that, okay. So now you observe that your x squared is equals to what? Your y squared, meaning your x is equals to what? Is equals to your y, okay. Your x is equals to your y there, okay. Then how then can we utilize this fact for us to determine what? Determine our value of x and our value of y. When it comes to this function, I can say it's 12 minus where there is y here, I'm going to put what? I'm going to put x. That would be what? 2x squared minus x squared is equals to what? Is equals to 0. So that would be like 12 is equals to 3x squared. Divide both sides by 2, I mean by 3, by 3 there. Your x squared will be equals to what? Will be equals to 4. Then the square root of 4 is going to be equals to what? Is going to be equals to x will be equals to positive or negative what? Negative 2. But I'm not interested in the negative value of x, because that will give me a minimum. So I've said my x is equals to positive or negative 2. So the only one that I'm going to use is a positive one. So I'll use positive what? I'll use positive 2. So I'll use the same when you substitute in this equation. That will give you what? The value of y. Your y is also going to be equals to what? Is also going to be equals to 2, because you have said your y and your x are what? Are equals to each other. Okay, your y and your x are equals to each other. So now, since you have your value of y, you have your value of x, Okay, we now need to determine what our value of z is, and we said our z, what equation did we say for our z was? Okay, we said our equation for z was equals to what? Was equals to uh, 12 minus, it was 12 minus xy divided by 2x plus what? 2y. So that would be like a 12 minus a 4. Why am I saying 4? 2 here, multiply them together, that will give you a 4. Divide by 2 by 2 plus 2 by what? By 2. That will give you what? That will give you a 1, because you have 8 over 8, it's a 1. So now you can come and say, okay, my volume will be equals to my x times my y times what? Times my z. So volume will be equals to what? 2 here multiplied by 2 multiplied by 1, giving what? Volume to be equals to 4 units cubic. Okay, and that's really how you go about those. So that's basically how we apply the extreme value theorem to either maximize or minimize the function that we're given. It's just a matter of us remembering how to apply the second partial test. But of course, in this case, even if you use the second partial test for it to confirm that the value that you have, because here we had your x is equals to positive or negative what? Negative 2, meaning even your y was what? Positive or negative 2. You have to confirm with you have to confirm that your positive 2 and your positive 2 for x and your positive 2 for y give you a relative max, because you're looking for the maximum volume. But I didn't have to do that, I already know, but you can try it out just for the sake of confirmation. But that's all in this video. Thank you very much for watching.